This is Math 1650, and this video is over section 5.2. We're looking at the binomial probability distribution, which is a type of probability distribution. So two requirements already exist. That is the summation of all probabilities associated with the random variable has to equal 1. And all probabilities with the random variable has to be between 0 and 1 individually. But there's going to be 4 more requirements that are going to be included in this. Okay. First, with the binomial distribution, we are looking at a situation where we only have 2 possible choices. And we're going to consider them success or failure a lot of times, but it doesn't necessarily have to mean success and failure given the situation. So we have 2 possible outcomes, and again we call them success and failure. And then for the probability of having success in one trial, it has to be consistent across all trials. So constant probability of success. So simplest idea would be flipping a coin. You have 2 possibilities, heads or tails. We can call head success or tail success, doesn't matter. But we call one side success, one side failure. And let's say we call head success. Probability of getting a head is 0.5, and every time we flip it, that remains be the case. And the third one is that we have fixed number of trials. And then the last one, which we won't really deal with a whole lot with because it's kind of taken care of when you do a sample, or when you sample it, everything. And that's independence. Basically, all trials will be independent of each other. Now, with these, the 2 possible outcomes, success and failure, we'll notate success with S. And its probability is going to be P, the probability of success. Okay. With failure, we'll notate that with an F. And its probability is going to be Q, probability of failure. Now, with the binomial distribution, you have 2 possible outcomes. You're going to decide which one's considered success, and you should be able to tell what that probability is. So knowing that you have this requirement means you should know exactly what P is equal to. And for Q is always going to be 1 minus P. So if we know what P is equal to, you automatically know what Q is equal to. Right, so P plus Q has to equal 1, because there's only 2 options, and we need a total summation of 1. And then the fixed number of trials, that means we have to know what the sample size is, or what N is. So N is our sample size, or number of trials. And then X is the random variable, and all possible values. P of X is the probability of the random variable. Of a probability of X where x is the random variable. Alright, so let's look at an example and check the requirements first for this example. Company manufactures small electronic components, and each component produced has a probability of 0.05% chance of being defective. In a batch of 20 products, let the random variable y represent the number of defective products. Does this meet the criteria for the binomial distribution? So, success. We can say success in this case would be a defect. And failure in this case would be no defect. Okay, now I know it may make sense to switch those two because a no defect would be a better, but in this case we are looking for defects, so we know how many defects there are and we know how many defects we're going to have. And so the random variable is representing the number of defects, which means S has to be a defect, or when you have a defect. Otherwise, your random variable will be representing the number of products without a defect. And then for a component having a probability of 0.05 for a defect, that means P is equal to 0.05, which means Q is equal to 0.95. Okay, so there's two possible choices. We just listed them. We have a constant probability of success based on a fact we know of P. Then we are looking at a batch of 20 products, so n equals 20. So this is fixed trials. And then we're going to assume each product is independent. So again, two choices. We have to be able to label success and failure. Constant probability of success. Fixed trials. And independence. Okay, now there is a formula for the probability of each random variable, and we would have to do this for every value. However, we won't be using this formula because we can do this on StatDisk much quicker for all values. Doing one of these calculations, it'll take a little time. Doing 20 different calculations will take a lot longer. Alright, so we're going to go into StatDisk here. Bring that up. To get to a binomial distribution on StatDisk, we'll go to Analysis, Probability Distribution, Binomial Distribution. Then we put in the number of trials. So in this case we have batch of 20. We put in the probability of success. So in this case it's 0.05. And then for the x value, we can look at these different values, but we don't have to put anything in here if we don't want to. I'll show you what I mean. If we hit evaluate, it's going to give us all possible values of x. So from 0 all the way down to 20. Okay. If we want a specific one, like let's say 2, we put in 2, it'll give us just that line. Okay. And then we can always take it out or change it to find the next line. So we can put in 0. It gives us, do 0 again. Okay, so not doing that for 0. There. I don't know why it doesn't do that for 0. That's interesting. Alright. 0 is going to be the top line. And so we have values of 0.358 for a probability of exactly 0 defects. Then we have the probability of x defects, that's 0.358 as well. For x or fewer, that means 0 or less than 0. Well, there's nothing less than 0, that's why that's the same. Or probability for x defects or greater, in this case it's 1.0. You're going to have anywhere from 0 to 20 defects. I mean, it has to be somewhere in that range. So that's why that's one or a definite probability. Right, so I'm writing these into these columns. P of x defects, P of x defects or fewer, P of x defects or greater. So just continue to write these in for 1, 0.3, and we'll take it to the third decimal for each one. 377, 0.736, and 0.642. And we'll do 2. 0.189, 0.925, 0.264, and the last one is 3, 0.060, 0.984, 0.075. Alright, so I have them all written in. Of those 3, you don't always have to write all of them out. Usually we're just concerned with whatever we're looking at to solve the problem. So what is the probability of having 2 defects out of 20? Now this is asking for exactly 2, and so we use the first column and we see that it's going to be 0.189. Or we can write this as 18.9%. What is the probability of having less than 2 defects out of 20? Now, less than 2 does not include 2. So that would be 1 or fewer. So we'll look at 0.736. Or 73.6%. If they have terms like less or more than, and that value is not included, you have to jump up to the next value. Remember, less than 2 is 1 or less. It would not be 1.5 or less because we are in the binomial or a discrete variable. So we can't have a 0.5. So we always just jump up to the next one or jump down to the one that we're looking at more than. What is the probability of having 2 or less? Now this would include 2. So we are looking at 2 or fewer, 0.925, 92.5%. What is the probability of having, what is the total probability of 0, 1, or 2 defects out of the products? So what that is asking is it's asking to basically find this total here. 0.358, 0.77, 0.377, and 0.189. And you get 0.924. Which is 92.4%. Now, there's a little bit of rounding difference, but these last two problems were basically the same value here, and the reason why is the probability of 2 or less means the total probability of 0, 1, and 2. So we could have just wrote the same number because, that's how the probability of X defects or fewer is found, by totaling up all the other probabilities. Right, the last thing, what is the probability of having 1 or more defects out of 20? For 1 or more is going to be the third column, and we're going to include 1, so we're looking at 0.642 or 64.2%. All right, so everything we deal with, we always go back to mean, variance, and standard deviation. Now, this has actually the easiest mean and standard deviations to calculate, and variance. Right, the mean is n times p, your sample size times your probability of success. The variance, it's even easier, well, maybe it's not easier, it's a little bit harder. N times p times q, multiplied by one more thing. And then that's the variance. And then the standard deviation is just the square root of the variance, so n square root of n, p, and q. So those are the three formulas for this. Right, so again, looking at our previous examples, we had p is 0.05, that means q is 0.95, and n is 20. So the average number of defects, or the mean, is going to be 20 times 0.05, which is equal to 1. The standard deviation is going to be square root of 20 times 0.05 times 0.95. And so you get square root of 0.95, which is 0.975. And then with this, we'll also look at minimum usual, maximum usual. So minimum usual, remember these are mean plus or minus 2 times the standard deviation. So 1 minus 2 times 0.975, and 1 plus 2 times 0.975. First one is negative 0.95, and the maximum is 2.95. Right, so if we're looking at whether 0 defects is considered usual, because we're negative, 0 is actually within the interval. So it's 0 is usual. Interval being from negative 0.95 to 2.95. Is 2 defects considered usual? Same thing, 2 is in the interval, so 2 is usual. And then is 3 defects considered usual? No. 3 is outside the interval. Right. Now again, we're dealing with defects. You're not going to have decimals here. You're going to be whole numbers, 1, 2, 3, or so on. So what's considered usual will be 0, 1, and 2. And can't have negative numbers, can't have decimals, can't have 3 or higher because that's outside of the interval. Now, with the mean, standard deviation, and variance, that also can be found on Status as well. Just click on results. It gives us those 3 values. And so you can see it matches up to what we found with the mean and what we found with the standard deviation. So easiest formulas still have an easier way of doing it by just looking at Status. Okay, so let's do another example. Pharmaceutical company receives large shipments of aspirin tablets and uses this acceptance sampling plan. They randomly select and test 24 tablets. Now, these tablets will be probably thrown out because they're being tested. So, no matter if they have a defect or not, they're not going to be given to the public. Right, so they test 24 tablets, then accept a whole batch of all the tablets they have. If there is only one or no tablets that doesn't meet the required specification, or you can say that has a defect. If a particular shipment of 1,000 of aspirin tablets actually has a 4% rate of defect, what is the probability that this whole shipment will be accepted? Alright, so if it actually has a 4% defect, we're going to see what the mean is, or what the actual number would be that would be defective. Let's get our values first though. First, let's make sure this is a binomial distribution. Your success is going to be, again, defect, and failure is no defect. Your probability of success is 0.04. Your probability of failure is 0.96. And your sample size is 24 tablets. And then we're going to consider each tablet to be independent. Alright, so first, let's look at the mean. Mean is equal to n times p. So this is 20. Actually, let's look at how many are actually defected in the total. That's what I wanted to find first. So total defects in shipment is equal to 0.04 times 1,000 is 40. Okay, so this 1,000 tablets have 40 total defects. Now, of the 24, let's find what the average amount, the probability. Let's do this one first. Let's find the probability that this whole shipment is accepted. So the probability is going to be the probability of 0 or 1. defects. So the probability of one or fewer is what we're looking at. So let's put this into the stat disk. So 24 tablets, 0.04 probability of a defect. Let's just take that out. And so one or fewer will be 0.7508. So second column, well, not counting the x column, of the probability columns, it's the second column, the probability of x or fewer. And then we're looking at one or fewer, so we're looking at the 0.7508 there, that particular column. You may not see my cursor, but I think you can see that. All right, back to this. All right, so in other words, we can say it's 75.1% chance of the whole shipment being accepted, even with the defects being 4%. Right, so there's 40 defective pills. You're going to find only at most one, and that means that in the shipment being accepted, there's 39 defects still in there. Right, what is the average number of aspirin tablets that would have a defect? So this is the actual mean of our sample n times p. So 24 times 0.04. Which is 0.96. Right, so 24 batch, 24 tablets, there's an average of being just less than one that you're going to find that has a defect. Standard deviation, square root of 24 times 0.4 times 0.96. And we get 0.96 standard deviation. So our usual value range, 0.96 minus 2 times 0.96, and 0.96 plus 2 times 0.96. So high value is 2.88. Low value is a negative 0.96. So anywhere from 0, 1, or 2 defects found is usual. Right. So 0 and 1, there's a 75% chance you're going to find that and still allow the shipment to go through. There is a chance though you'll find 2 and the shipment would not be allowed to go through. Too many defects basically. So now let's look at another example. This one deals with presidential elections. In a past presidential election, the actual voter turnout was 61%. Afterwards they surveyed 1,002 subjects to see if they voted in the election. Find the mean and standard deviation for the number of actual voters in the groups of 1,002. Right, so again, you either voted or you didn't vote, so there's your two choices. Your probability of success in this case is 0.61. So P is going to be 0.61. Q is going to be 0.39. So this is voting not voting. N is our sample size, 1002. So the mean, we can just do this on StatDisk. Kind of want to get both involved, and so you see how I do it both ways. 1002 and Q is 139. Oh, we don't need Q. Hold on. 0.61 is P. And we go to results. And so the mean is 611.22. Standard deviation is 15.44. Right, so I have those written down. So if 701 said that they voted in the last presidential election, is the result consistent with the actual voter turnout? Or is this result unlikely to occur with an actual voter turnout of 61%? Why or why not? So let's look at the minimum usual and maximum usual. So 611 minus 2 times 15.44. And you get 580.12. And then 611 plus 2 times 15.44. And you get 641.88. So 701 saying that they voted is unusual. So based on these results, does it appear that the accurate voting results were obtained? The answer is no. 701 is unusual, and seems to stem from a biased survey. Now, bias doesn't necessarily mean, I guess, bad. It could be that they went to a place where, maybe they went to a place, a political science course where a lot of people vote or something like that, and so they got more people involved that do vote for whatever reason. Or could it be just people lied? That could be another reason. Right, so we're going to go through some more on doing binomial probabilities. We're going to be using StatDisk for this. Now, what you can do is you can pause the video, try these, and see if you can understand, then come back and watch me go through the video so you know if you did it right or did it wrong. Or you can maybe watch a little bit and then go through. But all of this is going to be on StatDisk, and these are going to be more straightforward questions. So we're going to look at the binomial probabilities corresponding to a sample size of 5 and the probability of success of 0.1. So let's put this in the StatDisk. So 5, 0.1. Go ahead, evaluate. And so it's going to use the first column here for what we're going to find. We'll just look at the probability. So probability of 0 is 0.5904. 0.4900. Now I'm going to write these out because some of these are going to get really small. Probability of 1 is 0.3280500. Probability of 2, 0.072900. Probability of 3, 0.08100. And the probability of 4 is 0.000450. Now, be careful that you're going 0, 1, 2, 3, and 4, and 5, and you don't get caught up on the row numbers. This one starts out at 0, the row starts out at 1. And so if you're looking at the row number instead of the first column, your lines are going to be off. So let me go back to Zoom, and we see the values I have. Right, so now we're going to assume that boy and girl's births are equally likely, and we're going to find the probability of out of 75 random births, how many are boys. And so we're going to only look at, probability of getting 25, probability of getting 30, and the probability of getting 55. So 75 is our n, and equally likely means that it's 0.5 is our p. So we're going to put in 25. We get probability of 0.0013920. Then we can check 30. And we're going to get probability of 0.02069662. And then we're going to check 55. And we get 0.0000213. Alright, then the next one, let me bring in Zoom again, is we're going to look at probability of a boy being higher, 0.5121, compared to that of a girl who's at 0.4879. Again, we're going to look at 25, 30, and 55 and see how they changed. Right, so probability of a boy now is 0.5121. We'll start with 25. And we get 0.00 7435. So it's actually dropped. So 25 boys is a lower probability in this point. 30 would be 0.014082. That has also dropped. And 55 0.0000485. That has increased considerably for the probability it was. And that's those values. Okay, we don't have to look at the girl's probability because it's only asking about boys, and the girls would just be the opposite anyways, 1 minus any of these. Alright, we're going to do kind of the same thing, but now we're going to look at finding probabilities that are fewer than, or at most than, at least than, or more than. So it's a little different because we got to pay attention to exactly what column we are going to need here. So we'll go back to the equally likely, 0.5. We're going to do each one. So first one is fewer than 50. That is not including 50. So we need to do 49. And then we want 49 or fewer. So this one includes 49 or fewer probability. That's the 0.9973859. And if we compare this to a probability of 0.5121, it's going to be at 0.9951209. A little bit lower probability than before. Alright, so now let's do at most 20. So at most 20 is 20 or fewer. We'll put in 20. And let's do equally likely. Just go, so I go left to right. Alright. 0.0000325. And then 0.5121. It's 0.0000133. Stat this back up so you can see the values I have written. So 49 or fewer, pretty high probabilities for each of these. And 20 or fewer, very low probabilities, why we have to write them all out. Okay. When we find at least 45, we're going to look at 45 or greater. And we find more than 28, we're going to look at 29 or greater. Okay, so 0.5, we'll do 45 or greater. So that's the last column. 0.0526711. And then we'll do with the probability being 0.5121. That column is now 0.0792891. And back down to equal, we'll do 29 or greater. So for more than 28, we're looking at 0.9815225. And then with probability of 5.5121, we're looking at 0.9891522. Last one deals with eye color. Assume 40% of the population in the United States has brown eyes. If 16 people are randomly selected, so n equals 16, what is the probability that exactly 10 of them have brown eyes? Okay, p equals 0.4, and then we're going to look at x equaling 10. So 16, 0.4, x equaling 10, and we're looking at exactly 10. So the probability is 0.0391770. And then the probability that at least 10, meaning that this is 10 or fewer, at least 10 of them having brown eyes. At least 10, just want to make sure I have it right. No, sorry, not 10 or fewer. At least 10 is 10, 11, 12, so 10 or more. So 10 or greater is what we're looking at. So 0.058318. Go back to zoom and you can see what I wrote down. Alright, so that is the end of chapter 5. In the next video we'll start chapter 6 and start looking at continuous probabilities, or continuous discrete, the continuous random variables is what I mean. I'll see you then. Bye.